Hi everyone, I'm going to give you now some sample exercises that we can construct Venn diagrams on together. I'm going to do them on the board. Sometimes it helps just to see them done as opposed to reading about them being done. So we'll work through a few together. I'll explain them. The first couple of examples you're going to see in this series of little tapes will be more verbose than the latter ones. Once you get the hang of it, I don't need to say as much. So the argument I'm going to work on with regards to Venn diagrams in this first example is comprised of two universal statements, an all are, a no are, and no are conclusion syllogism. And the way that I'm going to work with this is, as usual, I draw my three circles. I draw the first circle, overlap the second circle, put the marker in the middle of the central part there, and draw my third circle. It doesn't have to be perfectly symmetrical. It doesn't have to be beautiful. Just enough to help you figure out what's going on when you try to read it. Then I'm going to start with my first premise, and I'll look at the first category of things that I'm going to chart will be computers. So I'm going to label this circle, the first circle will be the set of things that are computers. The first premise is all computers are machines, so our second category will be things that are machines. And the third circle down at the bottom will be thinking things, or things that can think. So I'll put TT for short. Now, here's what we're doing when we're actually working with a Venn diagram. What we're going to do is we're testing, since we're looking for validity, we're testing to see if, given the truth of the premises, if the conclusion can still be false. Remember our definition of validity. A valid argument is one where it is impossible to have all true premises and a false conclusion. So what we're going to do is we are going to chart and make the premises true on our diagram. And then we're going to step back and ask ourselves if the conclusion can be false given this diagram. So we don't chart the conclusion, we only chart the two premises. So let's start by doing premise number one. All computers are machines. If it is true that all computers are machines, I'm only looking at the computer circle here and the machine circle here. I'm going to ignore the third circle at the bottom. I'm only looking at these top two circles. If it's true that all computers are machines, that means anything in the computer circle must also be in the machine circle. That means there can be nothing out here. So I hatch through all of that section. Now, make sure you don't stop at this line. You go on through, because even though these are computers that also are thinking things in here, these would likewise be computers that are not machines. And in order for this first premise to be true, all computers have to be machines. So if there's anything in the computer circle, it must be in the machine circle. So you hatch out all the way down. Our second premise is no machines can think. So if it's true that there's nothing in the machine circle that will also be in the thinking thing circle, that means there can be nothing in this central area at all. Now, at this point I've made both of my premises true, and the question that I ask myself is, am I absolutely logically compelled to accept that conclusion, or could that conclusion be false? Well, the conclusion is no computers are things that can think. In making the first premises true, I was forced to say that there is nothing at all in this overlapping area. There's nothing in that central area. Since this is the empty set, the conclusion is no computers can think. It must be the case that there can't be anything in the circles of the overlap between computers and things that can think. So indeed, that conclusion is logically true, given the truth of the premises. So this argument would indeed be valid. Go on to the next one now to see another example.